Hello everyone, thank you for watching my video today. And in this video, we're going to take a look at finding the area of polar regions bounded by a single curve and finding the area of polar regions bounded by two polar curves. Okay, so let's talk about area of a polar region. We talked about with rectangular regions, dividing it into rectangles and using an integral to add up all the rectangles. So for polar, what we're going to do is we're going to divide up into sectors. And the area of a sector of a circle is given by the formula right here, half theta r squared. The development of formula for the area of a polar region parallels that for area of the region of the rectangular coordinate system, like I said. The primary difference is that in polar we use sectors instead of rectangles to partition off our region. All right, so on the next slide, we're talking about the function r equals f of theta, where f is a continuous and non-negative function on the interval between alpha and beta. The region bounded by f and the radial lines. Sorry about this. I don't know why my iPad is going crazy here. Let's try this again. Okay, there we go. Theta equals alpha and theta equals beta is what we wish to find. If we partition alpha to beta into n subintervals, blah, 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 this stuff we've done a lot, we do a summation, which turns into an integral. And this right here is our formula for an integral for the area in polar coordinates. Okay, so what do we got to remember here? If f is a continuous and non-negative on the interval, then the area of the region bounded by the graph r equals f of theta between the lines alpha and beta is given by 1/2 alpha to beta f of theta squared d theta. All right, so let's take a look at our first example. Find the area of one petal of the rose curve given by r equals 3 cosine 3 theta. All right, let's start here by just drawing a quick sketch of this. If you remember from your pre-calculus days, first of all, this is a rose. Anytime cosine n theta, it's going to be a rose. When n is odd, that's how many roses you get. So you're going to get 3 roses. If we put 0 in, we would get 3 times cosine of 0, which is 3 times 1, which is 3. All right, and then it's going to look like this. Sorry about the bad drawing here. Let's try that again. That's terrible. All right, one last try before I just forget about it here. That's not bad. Okay, so it's going to look something like that. We're going to try to find an area of one of those 3 regions. The easiest region would be this region right here. All right, so what we want to do, since this is actually, that region is divided up into 2 separate regions, what we're going to want to do is we're going to find the area from here to here. So just this area right here, and then double it. So we got to figure out what those bounds are. Well, this one we already said was going to be when theta equals 0. What is this point here? What's the first time where this equation would equal 0? That's when the cosine would equal 0. Okay? Cosine would equal 0 at pi over 2. So we want this to be pi over 2, which means theta is going to have to be pi over 6. If you put pi over 6 in here, you would get 3 pi over 6, which is pi over 2, which cosine of that would be 0. So that would be our theta. So what we're going to do is we're going to find the integral of this, and then we're going to double it to get our answer. Okay, so let's go ahead and do area is going to equal 2 times, we're doubling it, remember, don't forget, our formula, which is 1/2 integral from 0 to pi over 6 of f of theta squared d theta. So that's going to be 3 cosine 3 theta squared d theta. All right, the 2 and the 1/2 out in front cancel, so I'm left with 0 to pi over 6 of 9 cosine squared 3 theta d theta. All right, obviously we could do this with the calculator pretty easily, but we can also do this without a calculator. To do this without a calculator, you're going to have to remember something from your pre-calc days, which is our double angle formulas. Okay, one of our double angle formulas says cosine 2 theta equals, now there's three formulas that are cosine 2 theta. The one we're going to need here is 2 cosine squared theta minus 1. All right, and if I do some manipulation, if I add 1 divided by 2, I get cosine 2 theta plus 1 over 2 equals cosine squared of theta. Okay, so back to our problem here. we have cosine squared of 3 theta, which means this is going to be cosine of 6 theta plus 1 over 2. The 1/2 I can bring out in front. So now I'm left with 9/2, 0 to pi over 6 of cosine 6 theta plus 1 d theta. Okay, integrating that, we get 9/2. This is going to be 1/6 sine 6 theta plus theta from 0 to pi over 6. All right, so now we get 9/2, 1/2 sine 6 theta, so it'd be 6 pi over 6. Sine of pi is 0 plus pi over 6 minus 9/2. Put 0 in there, so sine of 0 is 0 plus 0. So we end up with 9/2 times pi over 6, which is 9 pi over 8 over 12, or 3 pi over 4. Now the other way to do this is just to not put this 2 here in the beginning, just find the 1/2, find the formula of that, and then at the end you can double it, and it'll give you the same answer, but we did it all at once, and it worked out just fine. All right, number 2, find the area bounded by a single curve. Nice thing about this one is the bounds are given to us here, pi over 6 to 5 pi over 6, okay? We're going to do this in a calculator in class to find this graph, but for now, that's the bounds that we're going to use, okay? So the area is going to be equal to 1/2 the integral of pi over 6 to 5 pi over 6 of our function, which is 1 minus 2 sine squared d theta. Okay, now this is going to be 1/2 integral pi over 6 to 5 pi over 6 of 1 minus 4 sine squared plus 4 sine to the 4th theta d theta. Oh, I copied on the problem wrong. I'm sorry. Just 1 minus sine. That makes it easier. This is just sine. This is just squared here then. I thought there was a squared here for some reason. I don't know why. So it's just 1 minus 4 sine plus 4 sine squared. Okay, now again, we're going to use another one of those double angle formulas here to integrate sine squared. The other cosine 2 theta formula, I should say the other, there's a couple of them, is 1 minus 2 sine squared. So with some manipulation there, we end up getting sine squared is equal to cosine 2 theta minus 1 all over 2. So I can replace this with cosine 2 theta minus 1 over 2. So I'm going to do a little copying here. This is going to be cosine 2 theta minus 1 over 2. Okay. Now we can continue on. So 1 minus 4 sine theta. 4 over 2 makes 2. So 2 cosine 2 theta. And if I distribute the 2 there, minus 2 d theta. And if I simplify any further, 1 minus 2 is just negative 1. Okay, and then if I integrate that, I would get negative theta, I forgot the 1/2 out in front there, times negative theta. Negative 4 sine, the antiderivative of that is plus 4 cosine. And the antiderivative of 2 cosine 2 theta would be negative sine 2 theta. The 2 on the 1/2 will cancel out from pi over 6 to 5 pi over 6. Now I'm running out of room here, but you get the picture. You're going to put 5 over 6 in, you're going to put pi over 6 in, you're going to subtract, and this is the answer we'll end up getting when we're done. Okay, this is an activity we're going to do in class here, so I'm not going to go through it in the screencast right now, but if you're watching at home and you haven't been in class yet for the notes, you can pause this video and try this activity. What should happen here is when you set these two equal to each other, you're going to get 2 answers. And then when we graph it, we actually will end up getting 3 answers. And the reason why is because we have to actually set this equal to 1 and -1 to find all 3 of our answers. Okay, but that's something we'll talk about much more in class when we get there. Okay, now let's talk about the region between 2 curves. Okay, so find the area of the region between 2 curves. Find the area of the region common to the 2 regions bounded by the following curves. R equals -6 cosine theta and R equals 2 minus 2 cosine theta. All right, first thing we should probably do is find the areas of intersection here. So -6 cosine theta equals 2 minus 2 cosine theta. If I add the 2 over here, divide, all right, we should get theta equals 2 pi over 3 and 4 pi over 3. Okay, so we can see here this is 2 pi over 3 right there, and this is 4 pi over 3 right there. Okay, we're trying to get the region common to both of those 2 regions here. So this little gray area, we'll call that A1. This little pink area here, we'll call that A2. And we're going to set up 2 separate integrals. We're going to add those together, and we're going to find just this area, just this area first, and then we'll double it to get the full area. So that's the thought process we're going to go through here. Just going to put that off to the side for now. Okay, so again, we're going to do A1 and A2. A1, we're going to call A1 this little gray area, A1, and then A2 is going to be that big pink area right there. Okay? All right, so A1 is going to go from this line to this line. All right, so it's going to be pi over 2 to 2 pi over 3. And then A2 is going to go from this line to this line, which is 2 pi over 3 to pi. So here we go. Area equals area 1 plus area 2. And then don't forget at the end, we got to double this because this is only the top half of our area. Okay, so area 1, 1/2 integral. We already said the bounds are going to be pi over 2 to 2 pi over 3 of -6 cosine theta squared. D theta. All right, now I'm not going to go through the work of doing that because we're going to probably end up using our calculator here at the end. We're going to get, when we're done with this, my calculator, so 0.8152-ish. Okay. Could we do that by hand? Absolutely, we could by the same thought process we did above. Okay. Area 2 is going to be 1/2. My bounds are 2 pi over 3 to pi, as we already said in our picture over there. And this time we're integrating the second function there, 2 minus 2 cosine theta squared d theta. Okay, again, I'm just going to type that in my calculator. We should get about 7.0387. So the area of this top half is going to be those 2 added together, which, give me a second to put my calculator here. So 0.8152 plus 7.0387, 7.8539. But again, remember, that's just half of it, so we got to double it. So our final answer here is going to be approximately 15.708 units. Okay. Last one here, find the area of the region between these two curves. R equals 3 plus 2 sine theta, and outside the curve, R equals 2. So the first thing we should probably do is find our points of intersection here. Sine of theta equals -1/2. Let's see here, that would be -pi/6, and well, I guess we could do 11pi/6 and 7pi/6. And if I set that equal to -2, we get that, which is not possible here, so don't have to worry about that there. Okay, so what we're going to do here is we are going to 11pi/6 is that line right there. If you can kind of see it hidden back there. Okay, we're going to call that -pi/6 because we're going to integrate from here to here, which is pi/2. And then what we're going to do then is we're going to double it because, again, it's only half of this full integrated region. Okay? All right, so we're going to do the area is going to be the area of the limacone. So I'm just going to put A sub L, and then we're going to subtract out the area of the circle, so A sub C. Okay, so the area of the limacone is going to be, and again, we're doubling this, right? So I guess we can do it now, or we can double at the end. It doesn't matter. So if I do it now, it's going to be 2 times 1/2 the integral from -pi/6 to pi/2 of our limacone. Okay, and then the area of the circle is going to be 2 times 1/2, and we're going to use the same bounds on that. Okay, obviously both these could be done pretty easily with a calculator or without a calculator. We could do them again using our double angle formulas that we learned in pre-calc. But for now, I'm just going to go ahead and type these in my calculator. Let's see here. We got this one would be 32.5646. This one would be 8.3775. And if we subtract them, our total area is going to be 24.187 square units, whatever that would be. Okay, so really the tricky part here is to find the bounds, and figure out what bounds you're going to use. Okay, and then just kind of go from there. Usually, if you're integrating on a sine axis, on the y-axis, you're going to do like the right side and then double it. If you're integrating on the x-axis, the cosine side, you're going to do like the top of it and double it. Okay? That's it for today's lesson. I hope you learned something new today. Thanks as always, and we'll see you again next time.